Hello, Proviso students, and welcome to the video notes on lesson 13.2, transformation of absolute value functions. These notes correspond with pages 589 through 600 in your math workbook. I'm going to do a combination of working on your math workbook and also doing notes straight into your spiral notebook. So let's begin. All right, first off, what is an absolute value? Absolute value, when you're asked to find the absolute value of a number, what it's being asked of you is you to answer this question: how many units is this number away from 0 on the number line? So, if you are asked what's the absolute value of, let's say, 5, then on the number line, 1, 2, 3, 4, 5, what's the distance? Well, it's going to be 5 units from 0 to 5. And if you're asked what's the absolute value of negative 3, how many units away from 0 is negative 3? 3. We don't care about the direction. We just care about the size, the magnitude of the change. Now, the absolute value function looks like this. F of x. What's the rule for some given input of x? That's what that symbol means. Equals the absolute value of whatever your input is. This is called the parent function. Because it is the most basic type of absolute value function we could draw or write. Now this is on page 589 in your book, what I'm doing right now. So if you want to go 589 in your book, you can fill in the information there. Now, I want to graph this parent function, and I'm calling that the parent graph. That's a term I made up for it. We always talk about the parent function or the graph of the parent function. I just combine those two together to make the parent graph. Alright, part A on 589 has us fill in a table of values. That is, for this function, if x is negative 3, then if your input's negative 3, your output's going to be the absolute value of negative 3 or 3. So on your graph, you're going to have a point at 3 comma negative 3. If x is negative 2 as your input, then when you take the square root of negative 2, you get positive 2. When x is negative 1, you take the absolute value. I'm sorry, I think I said square root. I'm at absolute value. You take the absolute value of negative 1, you get positive 1. When x is 0, the absolute value of 0 is 0. When x is positive 1, the absolute value of positive 1 is 1. 2 is 2, and 3 is 3. So that's part A's table. Make sure you have that filled in or copied in your spiral notebook like this. Either way, but make sure you know it's page 589. Indicate that in your spiral notebook. Part B, we want to graph this parent function. So here's my x-axis, here's my y-axis. What I'm doing is 2, 3, 2, 3, 1, 2, 3. Now, I have a point at the origin, 0, 0, from right here. Then I got point negative 1, 0, left 1, up 1, negative 2, 2, left 2, up 2, negative 3, 3, left 3, up 3. Then I have a point at 1, 1, right 1, up 1, 2, 2, right 2, up 2, 3, 3, right 3, up 3. When I connect these dots, I get a V-shaped graph. So if you want to draw, if you're working in your workbook, on page 589, part B, go ahead and draw that. If you are doing this in your notebook, once again, just indicate that this is on page 589. And then finally, part C. Part C asks where the vertex lies. Now, the vertex is the point that forms the V. It's where the two rays come together, intersect, that forms the V. Or, another way to look at it, it's the highest point or lowest point of your curve. So in this case, with our absolute value, lowest point is right there at point 0, 0. So the vertex, once again, highest or lowest point. So if my V opens upward, my vertex is right there. And if my graph, my V-shaped graph opens downward, which it can, we'll talk about that in a little bit, my vertex would be right there. Alright, so you were asked to do the discovery-based activity where you graphed a whole bunch of stuff, and you hopefully discovered some things. We're going to talk about that. So, in Explain 2, and once again, that's where I'm going to switch between the book and my notes. No, I'm sorry, Explain 1. And that's on page 590. They give us this generic form of the absolute value function. Where h and k are numbers, constants. And that's not a hashtag. That's the old-fashioned symbol for numbers. Before it's been co-opted by you young kids and your hashtags. Or if you watch Cobra Kai, hash browns, the guy likes to say. X is your variable. And more specifically, it's your input. Alright. You might have, hopefully, from the activity, the discovery-based activity, you've learned that the vertex of the absolute value function, and of the graph of any absolute value function, is always going to be h, k. So I'm moving from the origin with the parent graph to my new graph transform graph, and the vertex will be HK. So let's look at part A on page 590, and I'm gonna, because we did this activity yesterday, I'm gonna streamline part A. So part A, we have the equation g of x is equal to absolute value of x plus 3 minus 5. Alright, so I'm going to start off identifying where the vertex is of my new transformed graph from the parent function. And it's going to be the opposite of this. So that's positive 3. I'm going to move to negative 3. And my y value is going to be whatever I'm adding or subtracting. That doesn't change. Negative 3 comma negative 5 is where my vertex will lie. So for right now, with what we are doing, negative 3. 1, 2, 3, 5, 1, 2, 3, 4, 5. The parent function, well, you know what? Let me graph the parent function because I think you're asked to do that. I'll put the parent function in blue. So my vertex of parent function, the basic function, is at the origin, and then I get this v that goes up with the slope of positive slope of 1 to the right, and negative slope of 1 to the left. And that should be straight. There we go. Not easy if I go. It's a lot tougher for me to go from the left to right than right to left. I just train my brain that way. Alrighty. So there's our original parent function. That is the graph when we have y is equal to absolute value of x. Now what I want to do is transform this. So I'm going to have to move. My x coordinate is going from 0 to negative 3 on the x-axis. So what I have is a horizontal shift. I'm moving horizontally. Left 3 units. And then that negative 5 I'm adding, or that's being placed on at the end, I'm going to go down 5 units. So that's a vertical shift, because just like vertical leap, when you're fighting a vertical leap, you're jumping straight up and down. When you're going up and down, you're moving vertically. The horizon, when you look out along the horizon, everything's going side to side. So horizontal means going side to side. So horizontal vertical shift, we're going down 3. No, down 5, my bad. So my new vertex would be at negative 3 comma negative 5. And then nothing else has changed. The shape is the same. I go over 1, up 1. I go over 1, up 1. I go over 1, up 1. So I got my V. It's still going this way. And then to the left 1, up 1. To the left 1, up 1, etc. So it's basically like I'm coming up here, I'm moving this blue V over 3 to the left and then down 5, and I get it, it'll lie right on top of that black V. And that is my transformed function. Now let's look at B now, part B on this. No, still on. No, I'm on page 591 now. This equation or function is g of x is equal to absolute value of x minus 4 plus 2. So, what I want to do is identify where the vertex is going to lie for this transformed graph. It is going to be the opposite of this, which would be positive 4. And my vertical shift is, I'm going to move up or down, wherever that is. So I'm going to move up positive 2. Oops. So now I need to graph this. One, two, three, four. 1, 2. So I put my vertex at 4, 2. Then my slope's going to be positive 1 going to the right, so over 1, up 1, over 1, up 1, over 1, up 1, and negative 1 going to the left from the vertex. That will be the slope. So to the left 1, up 1, left 1, up 1, left 1, up 1, etc. Connect the dots. You get your graph. That's how you do that. All right, let's talk about if you're given a graph, what would your equation be? And now I'm going to do a combination of book and paper. All right, this is on page 592. So please go to 592 in your workbook. All right, part A on 592, we have this graph. I'll bring this over here. Identify where the vertex is. Well, the vertex for this graph is at 1, no. I notice that each tick mark is 2 in this graph. It goes 0, 2, 4, 6, 8. So my x coordinate's 2 and my y coordinate is 3. So I want to write my equation now. Remember, the equation is g of x is equal to absolute value of x minus h plus k. Now, when we talk about horizontal shift, the word horizontal starts with an H. This starts with the H. So you're shifting horizontal left or right. What your x value is when you're moving, when you've got horizontal shift, you're moving along the x-axis. So you're changing your x coordinate. The x coordinate will be the H for horizontal, and then k, that's the other one. That's the vertical. So this is my H, this is my K. So I'm going to have g of x is equal to absolute value of x minus whatever the h is, in this case 2, absolute value, plus 3. And that's it. And remember what I was saying earlier. We want to know this value here, this h, will always make what's inside the parentheses, the absolute value, equal to 0. Now let's look at part B here. Part B's graph right there. Once again, how's part B different? Oh, it is different. Okay, it's very similar. You know what? Let's find a different one. No, wrong section. My bad. Let's find a graph. Oh, never mind. All right. Since I'm over here, go to page. Sorry, I'm just trying to cover something up. 595. Page 595. Let's look at number 8. All right. Let me do this. Be easier for me, right? Number 8 on page 595. All right. Identify where the vertex is. Vertex is the lowest point here. That looks like it's at -3, -3. Dang it. All right, that's fine. It is what it is. So the vertex is at -3, -3. So I'm write my graph. My equation of this will be g of x is equal to absolute value of x minus, you could do it this way, that value, which would be -3, and then minus the vertical shift, right there, the v for vertical shift, and I'm running out of room, -3. Now, a minus negative becomes a plus, so that's where we get the opposite at -3, +3. The horizontal, the h, we want the opposite of that in here, and there's my answer. All right. So now we've graphed equations from using horizontal vertical shift. We wrote the equation with just horizontal and vertical shift graphs. Now let's look at one other component that you did talk or looked at during the your activity yesterday, and that is, what if there's a coefficient other than 1 in front of the absolute value? What I mean by that is, so far we've been talking about changing the parental graph by that. Well, the thing is, there is an invisible 1 right there. 1 times the absolute value of x minus h plus k. Well, what if I did this? What if, instead of keeping the absolute value, the coefficient at 1, what if that could alter? So, go ahead and write this down in your spiral notebook. We're introducing another constant, a. So now we got a, h, and k are numbers or constants, and x then will be the only variable in this equation or function. What's the impact of a on the graph of the base function? Well, I believe this was part 4 and 5 in that graphing activity I asked you to work on, and hopefully you discovered that if a is positive, that is, if a is greater than 0, our graph opens up. That is, it looks like this. A is positive. If a is negative, that is, a is less than 0, the graph opens down. That is, our V will be going downward. And that's A affects our parental graph two different ways. Opens up, opens down. That's the easy one to figure out. The other one is, does it make it skinnier? Does it stretch does it change the slope? Does it change the steepness of our V? And that's a little more. It's not that hard, but it's not as easy as, hey, if I have a positive number in front of the absolute value, if I have a positive number in this position here, it opens up. If it's negative, it opens down. That's pretty straightforward. If the magnitude or size, we don't care about the sign of the number of A, but if the magnitude, that is size, of A is greater than 1, then we have what's called a vertical stretch. And what this magnitude of A, mathematically, the way we draw that, or using algebraic symbols, that will be the absolute value of A is greater than 1. That's what the magnitude of A greater than 1 represents algebraically. That's how we'd write it. Alright, so what does that mean? It means that 1, 2, 1, 2, 2, 3, 4. Alright, let's say I have the parental function. Y equals absolute value of x. Then I have a slope of 1. Positive slope of 1 going to the right of the vertex. Positive slope of negative 1 going to the left. Because when x is 1, our output's going to be 1. When x is 2, negative 2, our output's going to be positive 2. Because I'm taking the absolute value of that input. Now, let's say I have y is equal to 2 times the absolute value of x. Well, what that means is, when x is 0, my y value is still going to be 0, so the vertex is still at 0, 0. But now, let's say x is 1 here. Then I'm going to have 2 times the absolute value of 1, which would be 2 times 1, which is 2. Notice, when x is 1, now my red point there is twice as high as this blue point right here. And likewise, when x is negative 2, then I'm going to have 2 times the absolute value of negative 2, which would be 2 times 2, which is 4. So this red point, oh shoot, my bad, when x is negative 2, will be twice, that red point will be twice as high as that blue point there. So when I connect my dots now, my red graph is going to be stretched upward away from the x-axis. It's being pulled up, and my graph is getting steeper or skinnier. This red part right here is twice as steep as this blue part, wherever my blue pen is. I don't even know. Shucks. Then this part right there. So you got vertical stretch. It's being pulled up. Now, the last component of this is if the magnitude if the absolute value of A, magnitude of absolute value of A, is less than 1, that means if A is between 0 and 1. If the absolute value of A is between 0 and 1, then we're going to have what's called a vertical shrink. Your book uses this. I'm not familiar with this terminology of a shrink. I'm used to it being called a compression. But what that means is what's going on is your graph is getting flatter. It's getting squished down toward your toward the x-axis. So let's do an example of that, and then we're done. Alrighty. I'm going to graph my parent function, f of x equals absolute value of x. So the right side goes off in positive direction with a slope of positive 1. My left side goes off in negative direction, it goes off, toward negative infinity with that. A slope of negative 1. Alrighty. So now, let's say I have f of x equals 1/2 the absolute value of x. So A now, and I could do negative. Let's do negative. Sure. Just going to change it around just a little bit. 1, 2. But you'll still be able to see it. So, if I take the absolute value of negative 1/2, the A coefficient, that's equal to 1/2, which is less than 1. So what's going on is, let's say, if x is 2, my y value is going to be 2. That is this point right here. For my altered, I can't call that f of x. Let me call that g of x. For g of x, if I'm going to let my input be 2, then g of 2 is going to be negative 1/2 times the absolute value of 2, and that'll be negative 1/2 times 2, which is negative 1. So I have a point at 2, 1. So going to the right 2, now I'm going to go down just 1, not 2. And same thing if I go negative 2 go 2 to the left from the origin, negative 2, I'm only going to go down, that should be negative 1. I'm going to go down 1. My graph's going to open downwards. But notice the rate of change, or the steepness. This line below, the one that's opening down, is flatter, less steep, than the orange line on top. So, since I have a coefficient whose magnitude is less than 1, just the size, we're not caring about the sign, my y values are going to be smaller than at any given input than the original parental function. All right. Now it's time for you guys to practice, and that's what we're going to get you doing.